Is faster-than-light travel possible? Can we ever break the cosmic speed limit? In this video, we delve deep into the most realistic theories and cutting-edge scientific concepts surrounding faster-than-light travel. From Einstein's theory of relativity to wormholes, warp drives, and the mysterious quantum realm, explore how modern physics tackles one of the most fascinating and mind-bending questions in science. Join us as we explore wormholes and the concept of spacetime shortcuts, warp drives, and how they might bend space to allow superluminal travel, quantum tunneling, and the puzzling phenomena of the quantum world, tachyons, hypothetical particles that could travel faster than light, the fascinating role of cosmic inflation and how it relates to faster-than-light expansion, cutting-edge research in quantum mechanics and general relativity that could one day unlock faster-than-light possibilities. This video offers a detailed breakdown of the physics behind these ideas, highlighting the most promising, scientifically backed theories on how humanity might break the speed of light barrier and explore distant stars. Make sure to like, comment, and subscribe if you're fascinated by the wonders of space travel, cutting-edge science, and the future of human exploration beyond the stars. Don't forget to hit the notification bell so you never miss an update on our latest videos. The idea of breaking the light speed barrier is a subject of immense fascination, not just within the domain of physics, but also in science fiction and popular culture. The speed of light in a vacuum, approximately 299,792,458 meters per second, or about 186,282 miles per second, is the ultimate speed limit in the universe, according to Einstein's special theory of relativity. This limitation poses significant constraints on our understanding of space travel, interstellar communication, and the physical laws of the cosmos. However, throughout history, both theoretical physicists and sci-fi writers have speculated about ways to break or circumvent this cosmic speed limit. While the laws of physics as we currently understand them do not allow for objects with mass to reach or exceed the speed of light, some interesting theoretical constructs and proposals offer possibilities, albeit speculative, that might permit faster-than-light travel or communication. These ideas explore the boundaries of known physics and often require us to rethink the structure of space-time, the behavior of energy and mass, and even the very nature of reality itself. In this analysis, I will delve into the most prominent and plausible theories surrounding the idea of breaking the light speed barrier, drawing from known physics, hypothetical frameworks, and speculative ideas. Each concept will be examined based on current scientific understanding, the challenges they face, and their potential implications. Special relativity and the light speed limit. Before exploring how one might break the light speed barrier, it's important to understand why such a barrier exists in the first place. Einstein's special theory of relativity posits that the laws of physics are the same in all inertial frames of reference, and that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This theory has been experimentally verified to an extremely high degree of precision. Key consequences of special relativity. Time dilation. As an object approaches the speed of light, time slows down relative to a stationary observer. At the speed of light, time theoretically stops for the object. Length contraction. The length of an object contracts along the direction of motion as it approaches light speed. Relativistic mass increase. The closer an object gets to the speed of light, the more its mass increases, requiring more energy to accelerate it further. This results in the need for infinite energy to accelerate an object with mass to the speed of light, which makes it physically impossible under conventional means. The speed of light represents a universal speed limit because, according to relativity, no amount of energy can propel a massive object to this speed. The faster you go, the more energy you require, and the mass of the object increases with speed, compounding the difficulty. Wormholes. Bypassing the speed limit via shortcuts in space-time. One of the most popular ideas in theoretical physics and science fiction for circumventing the light speed barrier is the use of wormholes, also known as Einstein-Rosen bridges. A wormhole is essentially a hypothetical tunnel connecting two distant points in space-time, allowing for shortcut travel between them. How wormholes work? Space-time curvature. According to general relativity, massive objects curve space-time around them. A wormhole is a theoretical construct where space-time is curved in such a way that a tunnel connects two distant regions. If one could enter a wormhole, they might theoretically emerge from the other side almost instantly, effectively traveling faster than light would take to traverse the same distance through normal space. Traversable wormholes. For a wormhole to be usable for travel, it would need to be traversable. That is, it would need to allow safe passage for humans or spacecraft. This requires that the wormhole be stable and that the forces within it do not crush or disintegrate whatever is passing through. Challenges with wormholes: exotic matter. The most significant challenge to creating a traversable wormhole is that it would require exotic matter, a form of matter with negative energy density. This kind of matter has not yet been observed, though quantum theory suggests it might exist in minute quantities. Stability. Even if exotic matter were available, keeping a wormhole stable enough for travel is another major hurdle. Most solutions to the equations of general relativity suggest that wormholes would be highly unstable, collapsing or pinching off as soon as they form. Causality violations. Wormholes may lead to paradoxes and violations of causality, such as time travel, creating concerns about their feasibility within a consistent framework of physics. While wormholes are mathematically plausible solutions in general relativity, there is currently no empirical evidence for their existence. Furthermore, creating and maintaining a wormhole would require levels of control over space-time and energy far beyond anything we can currently conceive. Warp drives, distorting space-time to exceed light speed. Another promising theoretical concept is the warp drive, most famously associated with the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. The idea behind a warp drive is to create a bubble of space-time around a spacecraft, contracting space in front of it and expanding space behind it. How warp drives work. Space-time manipulation. In this concept, the spacecraft itself never moves faster than light relative to the space around it. Instead, it remains stationary within a warp bubble, while space-time itself moves around the craft. By compressing the space-time in front of the bubble and expanding it behind, the craft could effectively travel faster than light from the perspective of an outside observer. Energy requirements. One of the most significant barriers to constructing a warp drive is the immense amount of energy it would require. The original Alcubierre model suggested that a warp drive would need more energy than the total mass energy of the observable universe. However, more recent work has revised these estimates down significantly, though the required energy is still far beyond current technological capabilities. Exotic matter again? Like with wormholes, a warp drive would require exotic matter to function. In this case, negative energy would be needed to stabilize the warp bubble and prevent it from collapsing. Current status of warp drive research. While the Alcubierre drive remains purely theoretical, there has been some progress in the area of warp drive research. Physicists have explored modifications to the original model that could reduce the energy requirements, though these still remain far beyond what is feasible with current technology. The idea of manipulating space-time in such a way is still speculative, and the existence of exotic matter is not yet confirmed. Tachyons, hypothetical faster-than-light particles. In the realm of theoretical physics, tachyons are hypothetical particles that always travel faster than the speed of light. Unlike objects with mass, which are constrained by the light speed limit, tachyons are thought to have imaginary mass and move faster than light by nature. Characteristics of tachyons' imaginary mass. Tachyons are proposed to have imaginary mass, a concept derived from complex numbers in mathematics, which means they could never slow down to below the speed of light. The idea is that while massive objects require infinite energy to accelerate to light speed, tachyons would require infinite energy to slow down to light speed, negative time. If tachyons existed, they could potentially violate causality, as their faster-than-light speeds imply they would travel backward in time from some reference frames, leading to paradoxes. Theoretical status. There is no experimental evidence for the existence of tachyons, and many physicists believe that their existence would lead to severe violations of causality, making them unlikely to exist within our universe. Despite this, they remain an interesting concept in theoretical physics, offering insights into the limitations of our current understanding of relativity and spacetime. Quantum tunneling and superluminal communication. In the quantum realm, particles can exhibit strange behaviors that seem to defy classical physics. One such phenomenon is quantum tunneling, where particles can pass through barriers that they should not be able to cross according to classical mechanics. In some interpretations, quantum tunneling appears to involve faster-than-light phenomena. Quantum tunneling. In quantum mechanics, particles are described by wave functions, which give the probability of finding a particle in a particular location. When a particle encounters a barrier, there is a small probability that it will tunnel through the barrier, even if it does not have enough energy to cross it in the classical sense. Some experiments suggest that the tunneling process might occur faster than the speed of light. Tunneling time. Debate. The interpretation of whether quantum tunneling involves superluminal speeds is a matter of ongoing debate. While the tunneling process itself is faster than expected, it does not necessarily imply that information or matter is traveling faster than light. The consensus among most physicists is that quantum tunneling does not violate the light speed limit, though some interpretations remain speculative. Superluminal communication and the no-signaling theorem. In addition to quantum tunneling, there are various ideas about how quantum entanglement, where two particles are linked in such a way that the state of one instantaneously affects the state of the other, might allow for faster-than-light communication. However, the no-signaling theorem in quantum mechanics ensures that information cannot be transmitted faster than light via entanglement alone. While entanglement appears to involve instantaneous action at a distance, it does not allow for faster-than-light communication or travel. The Casimir effect is a quantum mechanical phenomenon that results from the vacuum energy present in empty space. This effect arises due to the fluctuations of virtual particles in the quantum vacuum, and while the Casimir effect has been experimentally verified, its implications for faster-than-light travel remain speculative. In quantum field theory, even empty space is not truly empty. It is filled with fluctuations of virtual particles that momentarily appear and disappear. These fluctuations give rise to a form of energy known as vacuum energy. When two uncharged, parallel metal plates are placed very close to each other in a vacuum, they experience a small but measurable attractive force due to a difference in the quantum vacuum fluctuations inside and outside the plates. This is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948. The Casimir effect can be seen as creating regions of negative energy density between the plates, where the vacuum energy is lower than in the surrounding space. Negative energy is essential for certain theoretical faster-than-light travel concepts, such as wormholes and warp drives, where it could be used to stabilize space-time distortions and prevent collapse. Although the Casimir effect produces negative energy on a very small scale, it is of interest because it demonstrates that negative energy can exist, at least in principle. The challenge is scaling up this effect or harnessing negative energy in a way that is usable for technologies like wormholes or warp drives. The negative energy produced by the Casimir effect is extremely weak, and scaling this up to levels sufficient for space-time manipulation remains purely speculative. Current technology cannot generate or control negative energy in the amounts that would be necessary to make faster-than-light travel a reality. Despite this, the Casimir effect offers an intriguing glimpse into the possible manipulation of vacuum energy and space-time, which could, in the far future, play a role in developing technologies that bend or warp space-time for faster-than-light travel. Quantum field theory, or QFT, is a framework that combines quantum mechanics and special relativity to describe the behavior of particles and fields at the smallest scales. One of the key insights from QFT is that information, energy, and signals are all constrained by the speed of light. However, there are aspects of QFT, such as quantum entanglement, that hint at phenomena occurring instantaneously over vast distances, raising questions about the speed of information transfer in the quantum realm. Non-local correlations, quantum entanglement, allows two or more particles to become linked in such a way that the state of one particle instantly affects the state of the other, regardless of the distance between them. This has led to speculation that information might travel faster than light through this connection. However, no usable information can actually be transmitted via entanglement alone, as it would violate the no-signaling theorem in quantum mechanics. No-signaling theorem. According to the no-signaling theorem, even though entangled particles exhibit instantaneous correlations, these correlations cannot be used to send signals or information faster than light. The communication between observers still requires classical signals which are bound by the speed of light. Therefore, quantum entanglement does not provide a means to break the light-speed barrier for practical communication. Quantum field theory's limitations on superluminal travel. While quantum field theory respects the light speed limit for all massive particles and energy transfer, it also suggests interesting possibilities in areas such as vacuum fluctuations, Casimir forces, and quantum tunneling. None of these phenomena have yet been shown to violate the light speed barrier in a way that would allow for faster-than-light travel or communication, but they offer tantalizing hints that space-time itself might be more flexible than our current understanding allows. Faster-than-light communication theoretical proposals. Although faster-than-light travel remains firmly in the realm of speculation, there have been various theoretical proposals for faster-than-light communication that attempt to circumvent the constraints of relativity. Quantum communication and the no faster-than-light rule. Quantum entanglement. As previously mentioned, quantum entanglement offers a form of instantaneous connection between particles, but it does not allow for faster-than-light communication due to the no-signaling theorem. Some have speculated that there might be deeper, as yet unknown principles of quantum mechanics that could allow for superluminal communication, but no experimental evidence supports this idea. Quantum teleportation. Quantum teleportation is a process by which the quantum state of a particle is transferred from one location to another without the need to physically transmit the particle itself. This has been demonstrated experimentally, but it still relies on classical communication, which is bound by the speed of light to complete the process. Therefore, quantum teleportation does not allow for faster-than-light communication either. Superluminal signaling via tachyons. As previously discussed, tachyons are hypothetical particles that always travel faster than light. If tachyons exist, they could, in theory, be used to transmit signals faster than light. However, tachyons lead to paradoxes involving causality violations, such as messages arriving before they are sent, creating grandfather paradoxes and other logical inconsistencies. Theoretical physics has not yet resolved how to deal with such paradoxes, and there is no experimental evidence for the existence of tachyons. In recent years, some physicists have explored the possibility that modified theories of gravity or extensions of general relativity might allow for faster-than-light phenomena. These theories often involve changes to the structure of space-time or the properties of gravity on very large scales. Modifying general relativity extra dimensions. Some models, such as string theory or brane cosmology, propose the existence of extra spatial dimensions beyond the familiar three. In such models, it might be possible for faster-than-light travel to occur by taking shortcuts through these extra dimensions. This is similar to the concept of wormholes, but involves entirely different mathematical frameworks. Brane world cosmology. In brain world models, our universe is a three-dimensional brain embedded in a higher dimensional space. Gravitational effects in this model could potentially allow for faster-than-light interactions or travel across different brains, though this remains speculative and highly theoretical. Higher dimensional gravity. Some physicists propose that gravity might behave differently at very large distances or in higher dimensional settings, potentially allowing for faster-than-light travel or communication. However, these models are still in their infancy, and there is no experimental evidence to suggest that they could offer practical solutions to breaking the light-speed barrier. Gravitational waves and faster-than-light effects. Gravitational waves. Detected for the first time in 2015, gravitational waves are ripples in space-time caused by the acceleration of massive objects such as merging black holes or neutron stars. While gravitational waves themselves travel at the speed of light, some theorists speculate that certain interactions involving gravitational waves might provide clues to faster-than-light phenomena, such as by manipulating space-time in ways we do not yet fully understand. Modifying the speed of gravity. Some speculative ideas suggest that under certain conditions, gravity itself might propagate faster than light. However, these ideas are highly controversial and have not been confirmed by observation. Current models of general relativity suggest that gravitational waves, like light, travel at the speed of light. Cosmic inflation and superluminal expansion. While no massive object can travel faster than light in normal space, the universe itself expanded faster than the speed of light during the period of cosmic inflation, just after the Big Bang. This superluminal expansion of space provides an example of how faster-than-light phenomena might be possible, albeit on cosmic scales and under very specific conditions. Cosmic inflation and faster-than-light expansion. Inflation theory. Cosmic inflation refers to the rapid exponential expansion of space in the early universe, occurring in a fraction of a second after the Big Bang. During inflation, space itself expanded faster than the speed of light. But this did not violate relativity because it was space expanding, not objects moving through space. Implications for faster-than-light travel. While cosmic inflation shows that faster-than-light expansion is possible for space itself, it does not offer a mechanism for objects within space to travel faster than light. Nonetheless, it provides an interesting precedent for the idea that space-time can expand or contract in ways that bypass the normal speed limit. Applications of cosmic expansion to faster-than-light travel. Some theorists have suggested that if we could harness the same principles behind cosmic inflation, we might be able to create regions of space-time that expand or contract faster than light, potentially creating a bubble around a spacecraft that could travel faster than light. This is conceptually similar to the idea of a warp drive, but would involve manipulating the fabric of space-time on a cosmic scale far beyond our current technological capabilities. Theoretical constraints and the future of faster-than-light research. While many of the ideas discussed above are speculative, they highlight the cutting-edge areas of theoretical physics that explore the limits of known science. Faster-than-light travel remains a tantalizing possibility, but as of now, it is not supported by empirical evidence. The barriers imposed by relativity, energy requirements, and causality violations are significant, and overcoming them would require a paradigm shift in our understanding of physics. As it stands, breaking the light-speed barrier requires not only new technologies but potentially new physics altogether, concepts that go beyond our current understanding of space, time, energy and gravity. While speculative concepts like wormholes, warp drives and tachyons offer exciting possibilities, they remain firmly in the realm of theoretical physics and science fiction due to their immense technical and theoretical challenges. The requirement of exotic matter with negative energy, the potential for causality violations, and the vast energy demands are formidable obstacles that we are far from overcoming with today's technology. In addition, ideas such as quantum tunneling, entanglement, and modifications of general relativity hint at ways the universe might allow for faster-than-light phenomena in specific constrained situations, but none provide practical means of breaking the light-speed barrier for objects or information. Even if we develop new ways of understanding spacetime or energy, any solution to this problem will likely take centuries or even millennia to materialize. For now, the speed of light remains the ultimate speed limit in the universe. But as history has shown, many impossible feats have been achieved through scientific progress. While faster-than-light travel or communication may seem unattainable, continued exploration at the cutting edge of physics into quantum theory, spacetime, and cosmology could one day open doors that we currently consider closed. In conclusion, breaking the light-speed barrier is one of the most profound challenges in modern physics, requiring not only advanced technological solutions, but also a deeper understanding of the very nature of reality. Though currently constrained by the laws of relativity, the quest for faster-than-light travel will continue to push the boundaries of our knowledge, and who knows what future breakthroughs may allow humanity to explore the stars in ways that are today only the stuff of dreams.